So the roof of a building here, that's a plane. Any two-dimensional and a three-dimensional, right? A piece of paper is one portion of a plane. A plane could go on to infinity, right? This could go on forever, but obviously it's cut off just for that roof. Notice how we've got a grid in there and some vectors. So here's an example. If we assume that the base of vector A is at the origin, right, then the white dot on the roof can be explained. So you have to get up to a point on the plane, and then you travel along in 2 dimensions on that plane. Okay, so here the dot is a little bit off. Half of P, so this is 1, 2, 3, 4, 5, 6, 7, 8 is 1, 2, 3, 4. So there, gets us up to here. That's half of P. And then 5/7 of Q. 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5. Really that dot is more like here. But in this case, we have to be on the plane, and then we travel this vector plus this vector to get to that point. Now, any combination of these, P and Q, will get you every point. So I could do 1/8 plus 1/7, I get that point. 2/8, 2/7, I get that. You can get every point along there. So these are your parameters. But just like an equation of a line in 2 dimensions, vector equation, you need to get up to a point on that line, here up to a point on the plane. So this is your position vector. And then you travel some multiple of each of those vectors that have to be going in a different direction. So P and Q can't be parallel vectors. If they were, then really this is a line, okay? Because if they were parallel, you'd keep going in the direction of a line. So any tile on the roof can be described using the equation vector. So R equals A plus alpha P plus mu Q, and the appropriate values for gamma and mu. Lambda, sorry. In any case, there are restrictions. So remember, definitions, parallel vectors are vectors with the same or opposite direction. So we cannot use parallel vectors. A zero vector has a magnitude of 0 and an undefined direction. So they also can't be zero vectors. Okay. So therefore, any plane can be defined by that equation as long as P and Q are non-parallel and non-zero. If either P or Q, not both, are zero vectors, or they're parallel, then this will represent a line. That's what we just talked about. Right? If both P and Q are 0, then it represents a point. So we're never going to have that situation. If you're coming up with a vector equation of a plane, just make sure those direction vectors are not parallel and not 0. Okay, so then what's interesting about a plane that we're going to get into a little bit, there's a plane drawn for you. There's a point A, so your direction, your position vector, I should say, gets you, so that's vector A gets you to that point. And then you've got your vectors B and C, okay, that are non-parallel. N here is perpendicular to the plane, okay? The name for a perpendicular vector is a normal vector. So we don't really use perpendicular as much, okay? We call it the normal vector. It's perpendicular to the vector B and to vector A, actually. Okay, if you can draw that. That's right, vector C. Maybe I'll take off A here. You can see that a little bit better. So that's perpendicular, and then here. Okay. Shows it a little bit better if you show both of them. And you can see what happens. He's going to sit down and show you. Oh, don't want that here. So, if you have, where is it? There's your 3 dimensions. You can kind of see it's a little bit darker blue there. So the blue vector and the green are your non-parallel vectors on the plane. And this turquoise is the normal to it. Okay, so if we move these around, okay, if I extend this out, try to have a good hand, really if I'm changing, if I'm just making the green longer, it's not really changing the plane. If I have a steady hand, okay, it's still going the same direction. If I change the blue, it's just changing that normal is going longer. Oh, it's a little bit, I don't have a great steady hand, but you can see that that's still perpendicular. If you want to rotate, no, that's not rotating the plane, so I just said. Better up here, actually. Let's go to this one here. So this one is just showing the normal. And so if I change the direction of the normal, it's changing the plane. This one actually works a little bit better. But this one doesn't show the 2 vectors on the plane. But you can see that no matter what orientation that normal vector is, it does look perpendicular to the plane, okay? And so if I had a better, maybe this one works a little bit better. This only shows 1, but if I move that, you can see it. Compared to that turquoise, it does look like 90 degrees. It's just this one, for some reason, I can't. It's moving the whole thing. Yeah, anyway. Okay, but if we were to calculate, it would be 90 degrees to each of those vectors. So to start out today, that's going to help us with coming up with the equation of a plane. Then we're going to learn something better to help us come up with a Cartesian equation of a plane later in the week. But for right now, take a look at the example. Okay, so that's a vector equation of a plane. So it's got its position vector and 2 direction vectors. And it says determine the normal vector of the plane. Okay, so what we know is that normal is perpendicular. So the dot product of the normal with each direction vector has to be 0. Okay, so what I would do is maybe let n, you could let it be unknown values, just A, B, C is fine. And so then n with direction vector, each one is 0. So first would be A, B, C, dot product with the first direction vector, 1, -1, -1. So you do get an equation. It's got 3 unknowns, each component of the normal vector. All right. Then what also has to happen is that it has to be perpendicular to the other direction vector as well. So now A, B, C with dot product with 2, -1, 1 also has to equal 0. Because remember, if you have, so So really, if this is your direction vector, I'm looking for a perpendicular to it. So this perpendicular here, maybe this is on my plane, okay? That's what I want. But if I'm just doing this green, and I put that there, that's still at 90 degrees, and that's not what I want. Right, so I just keeping it to one calculation there, and saying choosing an A and a B value is not going to give you enough information. Yeah, it would be perpendicular to the green, but I need it to be perpendicular to the plane. So then by checking with another direction vector, now I need that to be perpendicular to the green. So if I chose that, that's not perpendicular to the pencil, but this is perpendicular to both. So that's why I need both calculations done. One of them is not enough. Okay, so that's two equations in three unknowns. So we want to solve that, at least get it down to two unknowns. So I would solve this system and, let's say, get rid of the c's because they're opposite sides. Okay, there's no stipulation on the size of that normal vector. So you can just you don't have to let A or B be a parameter, like we kind of talked about when we were solving systems the other day. You can just let A and B, or sorry, in this case, A or B be one value, okay? I would try to make it something so that you don't have fractions. So for example, maybe here, if I let B be 3, then I know I'm going to be able to divide by 3. So I'm going to let B equal 3. So then I would have 3A equals 2 times 3. A equals 2. And then substitute them back in to get C. So 2 minus 3 is negative 1. So C is negative 1. So therefore, the normal vector is, or a normal vector is 2, 3, negative 1, or any multiple. So then for the Cartesian equation to the plane, or of the plane, you want to think about what we did for Cartesian equation of a line. In 3 dimensions, we found, 2 dimensions, we did that back in Math 20. 3 dimensions, we found the parametric equations, and we let the parameters be equal to each other. So kind of on that same process, except we have 2 parameters this time. So here we would have x equals 1 plus lambda plus 2 mu, y equals 2 minus lambda minus mu, and z equals 3 minus lambda plus mu. Okay, so then I would like to get rid of at least one of the parameters. So maybe solve 2 equations separately. So maybe in this set here, if I were to add these, then I can get rid of lambda, right? So I would get x plus y equals 3 plus mu. And then get rid of lambda, the same parameter. So if I got rid of lambda here, then I could get rid of lambda here, again by adding. So these ones by adding, I would have x plus z equals 4 plus 3 mu. And then you could eliminate mu or use substitution. Okay, so this into here. Right, so if I solve for mu here, I get and then I would have x plus z equals 4 plus 3 times x plus y minus 3. So I've got 3 equations, and really 1, 2, 3, 4, 5 unknowns. Solve 2 together to get it down to 3, 4 unknowns. Those 2 together get it down to x, y, and z, right? And then get all the variables on one side. So that's going to be, you need to have the x term being positive to be in simplest form. So if I bring the x over, I would have 2x plus 3y minus z, and then the numbers, that's negative 5, bring it over to the left, would be positive 5. Okay, that's the Cartesian equation of a plane. Again, we're going to learn a faster way of doing it, but that is, for now, for what you know so far, this is going sort of from first principles in a way, right? How to calculate, or how to determine the equation of a plane. Take a look at the coefficients here. Okay, 2, 3, negative 1. Take a look at your normal vector. 2, 3, negative 1. So that's where the easy part comes from. If you know the normal vector to a plane, you know almost all of the equations, right? So the normal vector to the plane are the coefficients of x, y, and z. The only thing you would be missing is you need to calculate that constant term. So you would at least have all the parallel planes to each other. And the constant term would be based on more information that's given to you. Okay? So that's what you want to realize. The normal vector to the plane are the coefficients of the x, y, and z terms in the Cartesian equation of a plane. Okay, so each component of the normal vector is the coefficient of the corresponding term in the Cartesian equation. Okay, so we know now what the form of a vector equation of a plane is. Position vector plus multiples of two direction vectors. We know what the Cartesian equation looks like. And now a third version is called the normal, the normal equation of a plane. There. So basically based on our information here, we call P a position vector. R is the position vector of another point on the plane. So if you think about a plane here, so here's your point P, here's your point R, there's vector P, vector R, right? And in this case, this is your general point, right? That gets you to X, Y, Z. All right, so the difference between those, this vector here, is a direction vector on your plane, okay? So R minus P, dot product with the normal vector coming out, we know it has to be 0, right? The normal vector has to be perpendicular to any vector on the plane. If we just use our distributive property, then that's going to be R dot n minus P dot n equals 0. And just rearrange that. That's the vector, the normal equation for a plane. This is X, Y, Z. Right? So that's sort of giving you every point. And so if you know the normal and a point on the plane, you can come up with the position vector of that and calculate this is basically that, by taking the dot product, gets you the Cartesian equation. So we really don't end up leaving it in that form that often. We use that to come up with our Cartesian equation. Okay. So here, kind of in general, here's your R, X, Y, Z, normal vector, naming the components A, B, C. Then if we use this normal equation, what is it going to look like? So that's going to be X, Y, Z, dot product with A, B, C, equals position vector, dot product with the normal. I'm going to leave that for right now because we don't know what the position vector is, so we can't come up with what it would be. If we take the dot product, and that's where we see our Cartesian equation, right? Coefficients of X, Y, and Z are the components of your normal vector. Then you can calculate what this is if you know a position vector on your plane. summarize here. There's your vector equation, okay? Parametric equations would be when you split them up, right? So x equals y equals z equals, so in this case that would be a1, let's say, plus lambda p1 plus mu q1. These are called parametric. Because their values depend on each parameter, right? Then the normal equation we just talked about. If your normal is defined as ABC, then there's your Cartesian equation. So a few different ways of showing that. So the first example is pretty straightforward. It says find the Cartesian equation through the point 1, 2, 3 with a normal vector. Okay? So you don't. What I would do in this case, if you're given the normal vector, you're kind of doing this right away. Or, well, actually, you can put it in here, but then you have to calculate what that is, still using the dot product. Okay, so you can go right to the Cartesian equation in that sense. Okay, so this is your, therefore your position vector is 1, 2, 3. Okay, so your coefficients for x plus 5y plus 6z equals your position vector. Oops. And then figure out what that is. And then just check, can you reduce it at all? So make sure your x, or whatever the leading coefficient is, so always put your x, y, and z terms in alphabetical order. And then make sure there are no fractions. And first leading coefficient is positive. Okay? Just like back in math 10. Next one. Now we have 3 points. So basically here we have a plane. We have A, B, C. Okay. So remember, we're finding the Cartesian equation. If we know the normal, then those are our coefficients. But in this case, so here, we want to get 2 direction vectors. So choose any 2 sets of those. It can be AB and AC, it can be BA and BC, whatever you want. Sometimes, even though I'm after the Cartesian, I like to set it up in as a vector equation, just to kind of see what's happening. So you don't have to do this, but I am going to. So if I can choose any of those points as my position vector. But again, the way I like to think about it is I'm going from the origin up to A and then traveling along these 2 vectors this way. So I'm going to use A. But again, it doesn't matter. And then for one of my direction vectors, I'm going to do AB. So AB would be 2, -1, -4, minus 1, 2, 1. So that's going to be 1, -3, -5. And then AC would be 1, 0, negative 1, minus 1, 2, 1. Okay. Now take a look at that. AC is 0, negative 2, negative 2. I could actually reduce that. Sorry? Oh, well, you just don't have to, like, show it fully in that form, per se. You could do it, I'm going to sort of do it from that form, but really, when we looked back at calculating the normal vector, if you just do these, and you call your normal vector, say, A, B, C, then find the dot product of AB with ABC, dot product of AC with ABC, and solve that system. Like we did here, right? So you could do it just by using the dot product to get your, now you have your coefficients. And then you would figure out what your constant term. So you don't have to do it this way. And again, we're going to learn a faster way later this week. But from here, from the vector equation, then you can come up with your Cartesian, your parametric, I should say, and put them into Cartesian. Okay, I'm going to keep it like this. You don't have to. I'm going to keep it with this not reduced, just to see how that plays out in terms of our equation. I guess I keep using Z. So x equals 1 plus lambda, y equals 2 minus 3, lambda minus 2 mu, z equals 1 minus 5, lambda minus 2 mu. Okay, so then you can, here, this one's already down to just lambda, so I could subtract these and then get rid of mu here. So I have y minus z is 1 plus 2 lambda. So from here you can do a little check, so you know your normal is 2, negative 1, 1. So take the dot product with each direction vector. So that's 2 plus 3 is 5, minus 5 is 0. 0, then 2 minus 2 is 0. And then also check your point, does it satisfy? So 2 times 1 is 2, minus 2 is 0, plus 1 is 1. So there's different ways of checking. Okay. Now, if you would reduce that to 0, 1, 1, Then you would have had fractions in here, okay, that you'd have to multiply through to get the proper Cartesian equation. Doesn't have fractions, okay? So actually turned out easier in this case. So you can always check your answers, right? And last one we're going to do today is the intersection. So example 4. So it says find the coordinates of the point of intersection with the plane. So you're given the Cartesian equation of a plane. So again, think about what that's going to look like. Intersecting with a line, right? There's 3 different lines there. So if this line is going like this, it's going to meet in one point. If this line is parallel to the plane, it's never going to meet. And if this line is on the plane, it's going to have an infinite number of solutions, where the solutions are the equation of the line, not the plane, right? So what intersects? It's infinitely many, but it's the actual line, okay? So 3 cases, point, none, and infinitely many with that equation of a line, okay? Well, probably, since there's 2 examples, there's probably one of each. Okay. What's nice about this Cartesian equation, you've got these in the lines in vector form because they're in 3 dimensions. So I would convert those to parametric form and then substitute in to see what parameter works or doesn't work. Okay, if there are no points of intersection or infinitely many. So here, x equals 1 plus 2 lambda. Now we can replace that in for x. We can replace y with lambda and z with 1 minus 3 lambda so that we get the equation just in terms of lambda. So we do get one value of lambda, which means there's 1 point of intersection, and now substitute it back in to actually find that point of intersection. So 1 plus 2 times negative 1. So 1 minus 2 is negative 1. Negative 1. And do the same for the next one. So you see the lambdas go to 0, and then you get 7 equals 11, which obviously it doesn't. So no points of intersection. Okay. What's a fast way of telling if a line is parallel, either there or there? To a plane. So if you have the Cartesian equation of a plane and you have a line, what's the fast way of telling if it's parallel? Yeah, take the dot product. Yeah. So dot product of this with this, so that would be 2 times 3 is 6, plus 2 is 8, minus 8 is 0. Okay? Unfortunately, it doesn't tell you, though, that whether it's there or there. Okay? But what you could do as well is you could say, okay, well, is this point, so once you've determined that it's this or this, does this point lie on this point? So 3 times 1 is 3, plus 0, plus 4. So 3 plus 4 is 7, okay? It doesn't satisfy it, so it must be this case. So this is the formal method, but if you're just randomly, well, not randomly, but if you're looking for does it intersect, you can do it in a faster way. Okay, so then this one has the same direction vector, so we know it's parallel, right? Then if you checked here, 1 for x, 2 for y, you do get 11 equals 11, so you know it's infinitely many. So that's a fast check, right? So say this test, and I might put a few multiple choice. So if it was something like that, you don't have to go through the whole thing, right? You can figure out what it would be without formal steps. That's where we're going to stop for today.